Hey everyone, we are looking at waves and electromagnetic spectrum today. So by the end of this lesson, you should be able to explain the emission of electromagnetic radiation in spectral form in terms of the Bohr model. So we're going to actually cover this standard in a couple lessons in this unit. So first, let's talk about the parts of a wave. So some terms you need to know here. Amplitude, which is noted by the capital A, is the height of the wave. So we're looking from baseline to the peak of the hill. How big is it? That's your amplitude. Wavelength, which is used for the Greek letter lambda, is the measurement from crest to crest, so from peak to peak, or trough to trough, which is lowest point to lowest point. And this is normally measured in nanometers. And then we have frequency, which is represented by the Greek letter nu, and this is the cycles in a given amount of time. So you would pick a point on your wave, and as it's moving, you would count how many times that point traveled through a wave in a given amount of time. And this is usually measured in hertz or per second. And then when we look at the electromagnetic spectrum, we're looking at a range of wavelengths and frequencies of all types of radiation that is electromagnetic. And when we're measuring this, we're looking sort of at we're looking at light in particular, light radiation. So we refer to this as photons, which are known as light energy. So this is what a wave looks like, okay? So you can see we've got high frequencies are when our waves are closer together, which means our wavelengths are very short. Low frequencies are when our waves are very far apart, which means they have longer wavelengths. So you can tell that they are inversely proportional here. And then our electromagnetic spectrum, let me X out of the video here, shows you the different types of radiations that we would look at and how we have weak ones over here with very, very low frequencies all the way over to gamma, which is very high frequency. So now let's talk about the calculations you need to know for waves and electromagnetic spectrum. So the first one is very basic. It's speed of light. It's represented by the lowercase c, and it's a constant value. So it is 3.0 times 10 to the 8th meters per second. This value is on your reference packet as well. Since it is a constant, we usually will use this calculation to solve for wavelength or frequency. So our formula is C is equal to lambda nu, so these are multiplied together. And one thing to know is when variables are multiplied together, it means they're inversely related. So that means when one goes up, the other goes down if they're equal to a constant value, which here they are. So make sure that your wavelength is in meters here. So it'll be given in nanometers. You will have to change it to meters because you want the meters to cancel with your meters in speed of light. Our other calculation here is for the energy of a photon, and this is E is equal to h nu. So that nu is frequency, E is energy, and h is Planck's constant, which is 6.626 times 10 to the negative 34th joules times second. This should also be on your reference packet. If, let's say, I give you energy, but I want to know wavelength, you can do that as well by substituting in your speed of light formula solved for nu or frequency. You can sub it in on how it would fit here. So actually, let me use this pen. This was a typo on my end. That should be your wavelength symbol at the bottom, not your frequency symbol. So if you want to solve for for wavelength, you can get rid of frequency by plugging in speed of light divided by wavelength and then solve for wavelength. So now let's go in and try some examples, I think. Yes. So we're going to calculate the frequency of a wave with a wavelength of 370 nanometers. So again, underline what you're given. Circle what you're looking for. Oops, well, press the wrong button. Okay. So remember, we've got to change it to meters so it'll cancel. So anytime you have a hundreds value nanometers, you can put the decimal after the hundreds place and then just tag on times 10 to the negative 7th. And that's how many meters it is. So you don't even have to do any math if you can remember that comparison there. So 370 nanometers is 3.70 times 10 to the negative 7th meters. We're going to plug that in and solve for V. So when you solve for V, I say V, you solve for nu, you need to get it by itself, which means you need to divide both sides by your frequency. So that's how we got our calculation over here. So we're going to do speed of light divided by our wavelength given. Remember, we divide our numbers out front and then we subtract our exponent. So it would be 8 minus a negative 7, which will be 15, but then you do our math here, you got to move your decimal. So we come out with 8.1 times 10 to the 14th per seconds. So you go ahead, let me X out of this picture. I want you to solve for the wavelength on a wave that has a frequency here. So pause the video and try that. All right, so now let's try another example. So now we're using our energy calculation. So we're looking for, or we see that a photon has a wavelength of 2.68 times 10 to the 6th per second. We want to know the energy. So we're using E is equal to H nu. And actually, I worded this one wrong. I'll tell you what, guys, I have done an issue with this. This should be a frequency. Sorry about that. I don't know why my typos are going all over the place. So we have a frequency of 2.68 times 10 to the 6 per second, which is right because that's the unit that we have here. So when we do that, we've got this set up with Planck's constant and our frequency. We see that our seconds cancel, which leaves us in joules, which is good because that's the energy unit that we have. It's okay, buddy. It's okay. So we're going to multiply those out and get our answer here. And now you can go ahead, pause your video, and try this bottom example here. Okay, and these are our last definitions to kind of look at for this lesson. So we have one called wave-particle duality, and this means that atoms will act as both particles and waves, so they exhibit properties of both. This is just a good idea to know because particles will move as waves. And then our other one is Heisenberg uncertainty principle, and this just states that you can't know the velocity and position of a particle at the same time. You can know one, but you will have no idea on the other. The closer you get to one value, the further you get from knowing the other. So very good, guys. Hopefully now you can explain the properties of energy